everyone. Thanks for joining. This is Esther Zhang, also known as Fengxue Zhang from Alibaba Academy. And I'm so excited to share our implementations of Enable System Standby with RISC-V Flying Phone, which will make RISC-V Flying Phone not just powerful, but power efficient. So today, I'll go through my topic through 4 parts. First, I'll start with the brief overview of what the system standby is with a technical reliance. And second, we're going through the 2 challenges that we have met during the implementation of a system standby and the target solutions that we have to make. Basically, it's about the power state coordination and the wake-up vector. Then we're going to look at our software framework and also the case study of our real product, RuyiBook JiaChen version. Then we'll end up with some the unresolved problems and the future roadmap that we're going to heading on. So without further ado, let's get started. So before I dive into my topic, I'd like to ask, what do you think what a system standby is? So the ACPI table defines the system states, separated them into 5 parts, from S0, which is the running state and wake-up state, to S5, which is a mechanical off. I'd like to narrow down a little bit about the scope of our talking about today to S3 and S4, which is the most particle in nowadays systems. So S3 is aka Suspend to RAM or system standby, and S4 is system to disk. So that when the system is going to in the standby state, all the context is going to save in the DRAM for S3 or the disk for S4. And when the system comes back, all things just restore from those memories. And then we'd like to ask a question, when we want to do this, what is the minimum things that we need to do? So maybe first we'll look at the right side height pictures. When you push your button on your laptop or on your phone, the sleep button, what happened? First, the kernel will just freeze all the stress in the system. Then it will suspend the devices, nevertheless of the peripherals or the cores, and non-boot cores, Then the boot core will last long enough to notify the system controller. And the system will go into deep sleep, and the system controller will leave awake to wait for the interruptions outside to notify that the system is going back to normal. And the resume process is just a reverse version of the suspend. I will not cover that into detail. So you can see here, all of the things relies on a well-defined software framework, as you can see here in the left-hand side. As I just told the story, there are main 3 characters: boot core, non-boot core, and system controller, which is RISC-V core in our context. And in XuanTie's context, it should be high-performance core C907 and the embedded core E902. So the core separated into different types of the firmware on the left-hand side. We got 3 layers. First, from the top to the bottom, first we will see the rich OS. In our context, it should be Linux. And then we'll see the privileged Flying Phone firmware. In our context, it's the OpenSBI. Then on the bottom layer is the Flying Phone firmware, where the system controller dominates. So you can see we got the full implementation of the software. What the key reliance that we need to do based on that? So we summarize 3 essential pillars that we need to be done. First, the device or the core power state transition. As I just told you that there is a suspend procedures in the sequence that the device and the core state has to be suspended. Then a standard software or hardware mechanism has to be supported. Then the wake-up vector has to be supported as well because the system controller has to wait for an interruption, outside interruption to resume the whole system. So you can see here on the left-hand side, we already have a well-defined software framework. So what is left? What's holding us back? So here's the challenging station that we have done to make the RISC-V system standby with more perfect performance. So I will start with, remember the story I just told you there were like 3 characters: system controller, non-boot core, boot core, and first I will go through the non-boot core. The non-boot core during the system standby and system resume procedures need to be hot plugged and hot plugged in. So for the soft firmware, I got to say it's already complicated and standardized. But for the hardware, it's hard to do so because XuanTie, as the CPU IP providers, it's hard for us to make our customers do these things standardized. So we can see a lot of the tricky blind phone specific power management procedures in our customers' designs, which will make us problems like you want to port one of the system into another, and you want the Linux kernel to be like a unique one, but if you let a lot of blind phone specific implementations in that, it will be hard to do that, right? So here's our solutions with the, this is a case study of our customers. I forget this session. As you can see here, when the CPU hot plug starts, it will transfer it into the OpenSPI. Then the OpenSPI has to notify the system controller, and when it is done, you have to go back to notify the kernel that it's done, which is a long process. We have calculated a number that one core needs to use 100 uniseconds. But think of a system we got the 64 cores. How many times is going to waste it on that, right? Which is unacceptable. So here we are, the PCU. We define the power management unit close to the core. So when the core dive into the deep sleep state, it will first notify the PCU that, okay, now I'm going to sleep. So when I went to the WFI state, please help me to power me down and clock at me. So everything just happened automatically. It's more like when you're going to sleep, you tell your cell phone, when I close my eyes, could you please help me turn the lights off? So everything just happened magically, right? So you can see here as a result, compared to the image I just showed you, what is missing here is a system blind phone specific firmware implementation just gone, which saves a lot of time on that. And saves the power management from redundant vendor specific hardware design implementation in the software. And the second, we remains 2 characters, right? We got the boot core and we got the system controller. Here we are. I'll start with the system controller. Remember the story I just told you that the system controller had to remain till the end, wait for the interruption from the outside. It's like a guard standing in front of the door. When someone knocks the door, you have to open that, right? So you don't want the sleeping guard, right? So some part of the system controller still need to remain active, which will cause power consumption. And another thing for the boot core, the boot core has to still long enough to notify the system controller. And after system controller resume back to the OSPM, it will release the boot core, right? But due to the security constraints, I will not let covered up deeply that, but due to the security constraints, the boot core has to reset from a fixed address. This hardware design makes no difference between the cold boot and the system resume. The cold boot could cost a lot of time because there are a lot of peripherals to initialize, like the DRAM, right? We need to train in it. But for the system standby and resume, we already have saved our context in the memory. Remember that we don't need to do that much of the implementations. So we don't want that things happen. So here's your solution for both of the questions. We got a PMU reference design in our SoCs. What it did is it will be notified by the system controller. With the system controller, before it went to WFI, a flag is to be set. Says that the system is about to go into sleep. The PMU will take over the system controller's work to monitor the system and make the system controller to sleep, in which case we will save the power. And then it will let the boot core to jump from another fixed address, which will let us bypass the cold boot process, in which cases the resume time is cut down. So with all our implementation I just shared, that here is our software framework adaptation. As you can see here in OSPM, we still have some self-designed protocols over here for the device suspend resume, which I will cover later. And in the privileged platform firmware, which is OpenSPI, we have implemented our hard suspend and hard resume, hard stop, hard start as the non-boot core, boot core, hot plug, and suspend resume in that. And the system suspend in the standard protocols as well. Also, the MPXY extensions for the communications of the intercore, like the AP cores and the system controller. And at the bottom, we got system device state machine transition and the wake-up vector configuration I just mentioned, and the system image and the fast boot. So here we are going to look at the results of that product. There is a RuyiBook. As you can see, you can find it on the back side of our booth. If you guys are interested, you can find our booth and play with the RuyiBook, play the system suspend. As you can see, the suspend power consumption is less than 10 milliwatts, and it will last long, 20 plus days, and the resume time is less than 500 milliseconds. Isn't it great? So we still got some unresolved problems in the future roadmap. As I just mentioned, that we got some self-designed software protocols inside the OSPM, because the standard RPM my protocols still have some of the implementation which is not provided, and we're going to provide it later, like the device suspend, power control suspend and resume. And also, I didn't mention that much, the CPU frequency, because when we suspend and resume, we want it to happen fast, right? So there was one more implementation that we have done during the procedure that we want the CPU frequency to stick on the faster one. But in our implementations, it still need to get into the system controller to change the frequency, which is the time costing as well. We are considering to do the same things like the PC use, make the hardware to do that. But if you guys got any other great questions, I'm happy that you can talk to me and we'll discuss. So here is our roadmap. So you can see here from the 2023, the SBI has upstream the system suspend support, and after 5 months, the XuanTie SDK just launched and doing the full implementation of a system standby. Then the RuyiBook JiaChen version released in a year, which is fast. Then the RPMI system protocols released in the 5 months. Still, you can see here, our XuanTie platform is almost grew up with the upstreaming RISC-V ecosystem. And in the future, we're going to work with the RPMI group as well. We're going to look at well, not just, you can see here, well, we're looking at IoT devices before, but later we're going to strengthen our more implementations like data centers, whatever it is. So we got ACPI table. We're going to support that in later, and the fixed hardware support as well. So for me, for right now, I'm working in the RPMI group. Yes, thanks for them to review my slides. I'm working in the service group of power monitoring and power capping. And for the devices power that I just mentioned, my TG teammates is going to cover that. That's pretty much of it today. And if you guys are interested to talk with me, and I'm happy to talk in the XuanTie booth. Find me. And any questions?
Hi. As part of your C5 entry, so at what stage actually your interrupt wake-ups can happen at any point of time, right? So in your hardware, at what point of time you start actually monitoring that? Is there no point of return you have in your hardware, or every sequence actually will keep on watching the interrupts and trying to go back to the active states?
You mean the other states in the power management, the system states?
You have a power off state where actually C5 state where you are powering off the overall CPU, right?
Yeah.
As part of that entry, you will keep on monitoring the incoming wake-up events as well, correct?
You mean the slides over here, the different type of CPU modes?
Yeah, the previous slide.
Yeah, so this one is just not used as in the CPU standby, but we use it in the CPU suspend in the running states. The power modes is to be seated before the core went to the FA type. So we got different types of flags to be seated. So if you want to go to the different types of power modes, you just set the different types of the flags to the PCU, tell them what type of suspend type I'm going to, and after you went to WFI, the hardware will do everything for you after that.
So when you start WFI, and you will keep on monitoring the wake-up event as well, right?
I understand your question. So the wake-up is also can be set inside of the PCB because it's not covered in the system standby, so I didn't mention that. But it also can be set. So if you're in a standard running states, you can set that you want to be outside, wake up by the I like to say timers, whatever that things that you want to be wake up from is configurable.